filmmakers can distill the intricacies of astrophysics and planetary science into relatable language. By breaking down technical processes like the transit method or radial velocity, audiences can grasp how scientists determine the presence of exoplanets and assess their characteristics. This approach not only informs, but also demonstrates the collaborative effort within the scientific community, bringing researchers' enthusiasm for discovery directly into people's living rooms. The pacing of a documentary allows for a deeper exploration of themes, encouraging viewers to ponder larger questions about life in the universe. By interweaving narratives of new discoveries with the historical context of our understanding of planets, filmmakers can emphasize our journey as explorers of space. This approach fosters a sense of connection, as audiences reflect not just on what exoplanets are, but also on what they represent, a beckoning call from the cosmos, inviting us to continue our quest for knowledge beyond the stars. Finally, the emotional resonance of documentaries can create a lasting impact. By telling stories of the search for exoplanets and the quest to find Earth-like conditions, filmmakers can evoke feelings of curiosity, hope, and awe. This emotional engagement is vital. It encourages viewers to appreciate not only the science, but the broader implications for humanity. By nurturing a sense of shared curiosity and responsibility for our place in the universe, documentaries can stimulate public interest in both astronomy and the critical nature of the scientific inquiry that continues to explore the cosmos. For centuries, humanity has gazed at the stars, seeking answers to our most profound questions. But with each discovery, we uncover even greater mysteries. From the mind-bending physics of black holes to the possibility of ancient alien visitors, our universe is filled with mysteries that challenge our understanding of reality. Join us as we dive into the most mind-blowing mysteries about the universe. When information, matter, or energy falls into a black hole, we encounter one of the most intriguing paradoxes in modern physics. Imagine a particle carrying detailed information about its properties, such as its position, speed, and unique qualities. As this particle crosses the event horizon, the boundary beyond which nothing can escape, that information seems to vanish from our observable universe. This scenario raises fundamental questions because the laws of quantum mechanics state that information should never be lost. The apparent destruction of information in black holes challenges our understanding of the fundamental nature of reality and the interplay between gravity and quantum mechanics. This apparent contradiction between quantum mechanics and general relativity is known as the information paradox. Stephen Hawking once proposed that information falling into a black hole could be lost forever. But this idea contradicts the principle of quantum determinism, which states that the past and future states of a system should always be determinable from its present state. Recent theories, including developments in string theory and the holographic principle, suggest that information might be preserved in some way. One idea is that information is encoded on the event horizon itself, much like a hologram, preserving the details without actually losing them inside the black hole. Another fascinating notion is the concept of Hawking radiation, where black holes can emit radiation over time and eventually evaporate. Some scientists theorize that information might slowly leak out through this radiation, albeit in a highly scrambled form. This complex interplay between quantum mechanics and general relativity remains one of the deepest mysteries in physics, fueling ongoing research and debate. Each step forward in understanding promises to illuminate not just the nature of black holes, but the foundational workings of the universe. Supermassive black holes, with masses ranging from millions to billions of times that of our Sun, are enigmatic giants residing at the centers of most galaxies. Their formation is still a topic of active research, blending several fascinating theories into a compelling narrative. One prevailing hypothesis posits that these colossal black holes started as smaller, intermediate mass black holes. Over cosmic timescales, they grew by voraciously consuming gas, dust, and even entire stars from their surroundings. This accretion process, combined with mergers between black holes, steadily built up their massive sizes. Imagine an insatiable cosmic entity continuously feasting on anything within its gravitational pull. Another theory suggests that the seeds of supermassive black holes may have formed very early in the universe's history, just a few 100 million years after the Big Bang. In these primordial conditions, giant clouds of gas could have collapsed directly into large black holes, bypassing the usual stellar-sized black hole phase. This process, often referred to as direct collapse, might explain how supermassive black holes appeared so early in the universe. Galaxy mergers also play a significant role in the growth of these black holes. When two galaxies collide, their central black holes can eventually merge, forming an even more massive black hole. The merging of these galaxies often drives large amounts of gas towards the center, providing additional fuel for the black hole to grow rapidly. Across billions of years, these Goliaths of gravity sculpt the galaxies around them, influencing star formation and the dynamics of galactic cores. Understanding their formation not only unravels the mysteries of these cosmic titans, but also provides critical insights into the evolution and structure of the universe. Hawking radiation, proposed by physicist Stephen Hawking in the 1970s, is a groundbreaking concept that combines principles of quantum mechanics with general relativity to explain a previously unimagined phenomenon. Black holes can emit radiation and, over exceedingly long timescales, gradually evaporate. Near the event horizon of a black hole, the boundary beyond which nothing can escape, quantum mechanical effects come into play. According to quantum theory, particle-antiparticle pairs are constantly being created and annihilated throughout space, even in the vacuum around a black hole. Occasionally, these pairs form right at the event horizon. In some instances, due to the intense gravitational forces, one of these particles may fall into the black hole while the other escapes into space. The particle that escapes carries away some energy from the black hole, effectively reducing the black hole's mass. This escaping particle is what we detect as Hawking radiation. Over incredibly long periods, this process causes the black hole to lose mass and energy. As it continues to emit Hawking radiation, it gradually shrinks, a process referred to as black hole evaporation. The full evaporation of a black hole is a slow process. For most black holes, especially the supermassive ones, this occurs over timescales far beyond the current age of the universe. However, for small black holes, the loss of mass can speed up dramatically as they get smaller, leading to a final burst of radiation before they vanish entirely. Hawking radiation not only provides a mechanism for black hole evaporation, but also bridges the gap between quantum mechanics and Einstein's theory of general relativity. It serves as a step towards understanding the deeper connections between the laws governing the tiniest particles and the largest structures in the cosmos. The idea of harnessing energy from rotating black holes is not merely the stuff of science fiction, but is grounded in fascinating theoretical physics. Rotating black holes, also known as Kerr black holes, possess an enormous amount of angular momentum and gravitational energy. This seeming paradox of tapping into a black hole's immense power was first proposed by physicist Roger Penrose in the form of the Penrose process. The Penrose process involves a particle entering the ergosphere, a region just outside the event horizon of a rotating black hole where space-time is dragged around at astonishing speeds. Within the ergosphere, it is theoretically possible to split the particle into two. One part falls into the black hole while the other escapes, carrying off more energy than the original particle had. In doing so, the process extracts a fraction of the black hole's rotational energy. Another fascinating concept is the Blandford-Zener-Jeck process. This theory suggests that magnetic fields surrounding a black hole could interact with its rotation, channeling energy out in the form of powerful electromagnetic radiation. Jets of high-energy particles, often observed emanating from the regions around supermassive black holes at the centers of galaxies, could be an indication of such energy extraction mechanisms at work. These theoretical methods present tantalizing possibilities but come with immense practical challenges. The extreme conditions and immense scales involved make actual energy extraction a daunting, if not currently impossible, engineering feat. Nonetheless, studying these processes enriches our understanding of black hole physics and the incredible forces at play at the edges of our scientific comprehension. While we may be far from building black hole power plants, these ideas stretch the boundaries of what we consider possible. propelling us towards deeper inquiries into the universe's most enigmatic entities. Whether or not we can ever directly harness this energy, the principles behind these processes continue to offer profound insights into the nature of space, time, and gravity. Should you find yourself falling into a black hole, your experience would depend greatly on the black hole's size and mass. For a stellar mass black hole, typically about several times the mass of our Sun, the journey would be extraordinarily violent and brief. However, falling into a supermassive black hole, millions or billions of times the mass of the Sun, could provide a longer, though equally unsettling, trip. As you approach the event horizon, the point of no return, the effects of gravity become extreme. For a stellar mass black hole, tidal forces, extreme differences in gravitational pull, would stretch and compress your body in a process whimsically called spaghettification. You would be elongated along the direction of the black hole's pull while being compressed along the other directions, quickly leading to your demise before you even reached the event horizon. In contrast, if you fell into a supermassive black hole, the longer distance to the singularity at its core means tidal forces at the event horizon would be less intense. You could theoretically pass the event horizon without immediate catastrophic spaghettification. As you fall deeper into the black hole, the view to the outside universe would shrink to a small, bright spot directly overhead, slowly fading as you approach the singularity where gravity crushes all matter infinitely small. Once inside the event horizon, the laws of physics as we understand them break down. Theories suggest time and space become interchangeable, leading to speculations about what might occur. Some suggest you could encounter the singularity where the matter is crushed to an infinitely dense point, ending your journey. Others hypothesize the possibility of reaching a region where space-time could connect to another part of the universe through hypothetical constructs called wormholes, or Einstein-Rosen bridges. Whether the final moments involve a rendezvous with a singularity or passage through exotic cosmic pathways, falling into a black hole remains a mysterious and perilously final voyage, an exploration on the very edge of our scientific understanding. Detecting exoplanets, the planets that orbit stars beyond our solar system, involves several ingenious methods, each leveraging different aspects of astronomy to unveil these hidden worlds. One of the most successful and widely used techniques is the transit method. When an exoplanet passes directly between its parent star and us, it causes a slight periodic dimming of the star's light. By carefully monitoring and measuring these dips in brightness, astronomers can infer the presence of an exoplanet, its size, and even some clues about its atmosphere. Another powerful method is the radial velocity, or Doppler technique. This approach relies on detecting tiny wobbles in a star's position caused by the gravitational pull of an orbiting exoplanet. As the planet orbits, it tugs on the star, causing it to move slightly towards and away from us. This motion shifts the star's light spectrum towards the blue end when it moves towards us and towards the red end when it moves away. By studying these spectral shifts, scientists can estimate the exoplanet's mass and its orbital period. The direct imaging method, though challenging, involves capturing actual images of exoplanets by blocking out the overwhelming glare of their parent stars. Using advanced instruments and techniques like coronagraphs or star shades, astronomers can isolate the faint light reflected or emitted by the exoplanet. This method is particularly useful for studying larger exoplanets that are relatively far from their stars, in regions where the contrast between the planet and starlight is less blinding. Another intriguing approach is gravitational microlensing, which takes advantage of the warping of space-time caused by a massive object, such as a star or planet, passing in front of a more distant star. The gravity of the intervening object acts like a lens, magnifying the background star's light in a specific pattern. If an exoplanet is part of the intervening system, its presence can be inferred from the distinct characteristics of the light curve. These methods, often used in combination, have led to the discovery of thousands of exoplanets, painting a diverse and fascinating picture of planetary systems far beyond our own. With each detection, our understanding of the universe expands, revealing the potential for worlds that might harbor life or offer conditions vastly different from those we know. Super-Earths are a class of exoplanets with masses larger than Earth but significantly less than those of ice giants like Uranus and Neptune. Typically, super-Earths boast masses ranging from about 1 to 10 times that of Earth. Their unique position in the planetary spectrum has captivated scientists, as they offer a window into diverse planetary formation and compositions. One reason super-Earths intrigue scientists is their potential similarity to Earth, which raises questions about their habitability. Many super-Earths lie within their star's habitable zone, the region where conditions might allow for liquid water to exist on the planet's surface. Water is a key ingredient for life as we know it, making these planets prime candidates in the search for extraterrestrial life. The composition of super-Earths can vary widely, from rocky planets with thin atmospheres to water worlds with deep global oceans. Studying super-Earths also broadens our understanding of planetary formation. Our solar system lacks planets with masses between Earth and Neptune, so discovering and studying super-Earths in other systems helps fill in gaps in our knowledge. These planets might represent a common step in planetary evolution, providing clues on why certain planetary systems evolve differently. Some super-Earths have intriguing atmospheric compositions, detected by analyzing the starlight that filters through their atmospheres during transits. This spectrum can reveal the presence of gases like hydrogen, helium, and potentially even more complex molecules. By studying these atmospheres, scientists hope to learn about the processes shaping these worlds, including volcanic activity, weather patterns, and potential biosignatures. Super-Earths embody a diverse array of worlds, each with the potential to challenge and expand our definitions of habitability and planetary formation. As our detection methods and technologies improve, the study of these planets will undoubtedly yield more surprises, deepening our understanding of the myriad possibilities within our universe. Rogue planets, or nomadic planets, wander through the galaxy unbound by any star. These mysterious worlds, existing in the dark expanse between stars, raise fascinating questions about the potential for life in such isolated environments. While the absence of a parent star presents significant challenges for sustaining life as we know it, certain theoretical scenarios suggest it might not be entirely out of the question. First, let's consider the possibility of subsurface oceans. If a rogue planet retains enough internal heat from its formation or experiences tidal heating from interactions with a large moon, it might possess a subsurface ocean insulated by a thick layer of ice. Similar to the icy moons of Jupiter and Saturn in our solar system, such oceans could potentially harbor microbial life or even more complex organisms, exploiting the energy from hydrothermal vents at the ocean floor. Another intriguing scenario involves thick atmospheres. If a rogue planet has a dense atmosphere rich in hydrogen or other insulating gases, it could trap enough heat to maintain liquid water on its surface or beneath a layer of ice. This atmospheric blanket would act like a giant thermos, retaining geothermal heat and potentially providing conditions suitable for life. This concept of atmospheric insulation expands the possible habitable zones far beyond the confines of starlight. Life may also arise from different biological principles than those on Earth. In the absence of sunlight, alternative energy sources, such as chemical energy from the planet's interior, might serve as the basis for an entirely different kind of biosphere. Extremophiles on Earth, microorganisms that thrive in harsh environments like deep-sea vents and acidic hot springs, hint at life's remarkable adaptability to diverse energy sources and conditions. Rogue planets push the boundaries of our understanding of habitability and challenge our perceptions of where life could exist. While the conditions are undoubtedly extreme, the resilience of life on Earth in similarly harsh environments suggests that life on rogue planets, though speculative, remains a tantalizing possibility. As our knowledge and detection techniques advance, these lonely wanderers might one day reveal themselves as harboring the secrets to life's adaptability beyond the stellar neighborhoods we are accustomed to. Searching for biosignatures on exoplanets involves using sophisticated techniques and instruments to detect chemical and physical signs of life from light years away. These biosignatures are essentially the indicators of biological processes that can be observed and measured from Earth or orbiting space telescopes. The quest for these telltale signs is one of the most exciting frontiers in modern astronomy and astrobiology. One primary method is the analysis of exoplanetary atmospheres, which can be done during transits. When an exoplanet passes in front of its host star, a small fraction of the star's light filters through the planet's atmosphere. By examining this light with tools like spectrometers, scientists can identify the absorption lines corresponding to specific gases. Certain gases, such as oxygen, methane, or ozone in particular, concentrations might indicate biological activity. For instance, on Earth, a combination of oxygen and methane in the atmosphere is mostly produced by life. Another approach involves the study of reflected light from an exoplanet, known as direct imaging. Instruments use advanced techniques to block the overwhelming light from the parent star, allowing astronomers to analyze the spectrum of light directly reflected off the planet's surface or atmosphere. Reflected light can reveal various surface materials and atmospheric components. Detection of unusual surface compositions, like chlorophyll-like signatures which on Earth are associated with photosynthesis, might provide clues about potential life. Additionally, scientists consider the possibility of detecting technosignatures, which are signs of advanced technology. These might include unusually structured light patterns or radio signals, akin to those our technology emits. Though the search for technosignatures is more speculative and challenging, the potential discovery of such signals would be a groundbreaking indication of intelligent life elsewhere. Groundbreaking missions like the Kepler Space Telescope and the James Webb Space Telescope, along with upcoming projects, utilize these methods to systematically explore exoplanets' atmospheres and surfaces. As our technological capabilities grow, so does our ability to detect subtle signs of life, pushing us ever closer to answering the age-old question, are we alone in the universe? With each advancement, the dream of discovering life beyond Earth moves from the realm of speculation to the cusp of scientific reality, making the search for biosignatures an exhilarating journey into the unknown. The Fermi paradox is a fascinating puzzle named after physicist Enrico Fermi, who famously asked, "Where is everybody?" This question encapsulates the seeming contradiction between the high probability of extraterrestrial civilizations existing elsewhere in the Milky Way galaxy and the lack of evidence or contact with such civilizations. Given the vast number of stars and potentially habitable planets, Fermi's simple yet profound query continues to perplex scientists and stimulate intriguing hypotheses. One of the central tenets of Fermi's paradox lies in the Drake equation, which estimates the number of active, communicative extraterrestrial civilizations in our galaxy. Factors such as the vast number of stars, many of which have planets in habitable zones, suggest that, statistically, intelligent life should be relatively common. Our Milky Way alone contains around 100 billion stars, many of which are orbited by planets that could host life. Yet, despite the seemingly favorable conditions, we have no conclusive evidence of extraterrestrial civilizations. Several theories attempt to explain this paradox. One idea is the possibility of the Great Filter, a hypothetical stage in the evolution of life that is extremely unlikely or difficult to overcome. This filter could be behind, meaning life rarely evolves to complex organisms, or ahead, suggesting advanced civilizations self-destruct before achieving interstellar communication. Either scenario presents sobering implications for our own civilization's future. Another hypothesis is the concept of the zoo hypothesis, where advanced extraterrestrial civilizations deliberately avoid contact with us, observing humanity from afar like animals in a zoo. They might be waiting for us to reach a certain level of technological or ethical maturity before making contact. Others propose that interstellar travel or communication might be inherently difficult or resource-intensive, limiting the spread or detectability of advanced civilizations. Additionally, some suggest that we might not be recognizing the evidence of extraterrestrial life because it differs significantly from our expectations. Life forms might be so alien in form and function that we fail to perceive their presence. The Fermi paradox remains a profound and open-ended question, driving both scientific inquiry and speculative thought. Each proposed solution, whether it leans towards biological, technological, or sociological explanations, brings us closer to understanding our place in the cosmos and the potential for others sharing it with us. The Great Attractor is a gravitational anomaly in intergalactic space that exerts a powerful pull on the galaxies in its vicinity, including our own Milky Way. Located roughly 150 to 250 million light-years away in the direction of the constellation Centaurus, this mysterious region is part of what's known as the Laniakea supercluster, a massive collection of over 100,000 galaxies bound together by gravity. The intrigue surrounding the Great Attractor arises from its immense gravitational influence. This gravity well is drawing galaxies towards it at velocities of up to several hundred kilometers per second. Observations indicate that entire clusters of galaxies are being pulled towards this enigmatic point. Even our local group of galaxies, which includes the Milky Way, is moving towards the Great Attractor at approximately 600 kilometers per second. Determining precisely what constitutes the Great Attractor is challenging because it lies within the zone of avoidance, an area of the sky obscured by the dense plane of our Milky Way galaxy filled with stars, dust, and gas. This obscuration makes direct observation difficult. However, advanced observational techniques and the use of X-ray astronomy have allowed astronomers to partially peer through this dense foreground. Research suggests that the Great Attractor is likely a major supercluster structure with large concentrations of galaxies, dark matter, and hot gas contributing to its intense gravitational field. One key structure associated with the Great Attractor is the Norma cluster, a massive cluster of galaxies situated near the center of this gravitational anomaly. Nonetheless, the full extent of what comprises the Great Attractor remains an active area of research. Understanding the Great Attractor not only helps us comprehend the motion of galaxies within our local cosmic neighborhood, but also provides insight into the large-scale structure of the universe. This region of space exemplifies the complex gravitational interactions that shape the cosmos, influencing the movement and distribution of galaxies across vast distances. Cosmic voids are vast, relatively empty regions in the universe, devoid of much of the matter that makes up galaxies, stars, and other celestial structures. These voids, some spanning hundreds of millions of light-years across, form an integral part of the large-scale structure of the universe, often described as a cosmic web of filaments and clusters, with the voids as the spacious gaps in between. The formation of cosmic voids is closely tied to the evolution of the universe itself. Following the Big Bang, the universe was initially a nearly uniform soup of particles and energy. Over time, slight quantum fluctuations in this primordial matter density grew due to gravitational attraction. Regions with slightly higher densities attracted more matter, forming galaxies and clusters. Meanwhile, less dense regions lost their matter to these denser regions, expanding into the vast voids we observe today. This process, governed by gravity and the expansion of the universe, has been ongoing for billions of years. Inside these cosmic voids, things are not entirely empty. Instead, they contain very low-density gas, some dark matter, and a sparse population of galaxies and galaxy clusters. The average density of galaxies in these voids is significantly lower than in the more densely populated filamentary structures. The galaxies found within voids tend to be smaller, less luminous, and often isolated compared to those in richer environments. These conditions can lead to different evolutionary paths for galaxies within voids, making these regions intriguing subjects for studying galaxy formation and evolution distinct from denser cosmic areas. Additionally, cosmic voids offer unique opportunities to study dark energy, the mysterious force driving the accelerated expansion of the universe. Since these voids represent underdense regions, they react more sensitively to dark energy, making them excellent natural laboratories for probing its properties. Cosmic voids, while seemingly empty, are rich with information about the universe's formation, the distribution of galaxies, and the enigmatic nature of dark energy. Their study continues to deepen our understanding of the universe's large-scale structure and the forces shaping its evolution. Galaxy filaments are colossal, thread-like structures composed of galaxies, gas, and dark matter, forming the backbone of the large-scale structure of the universe. These filaments can extend across hundreds of millions of light-years, connecting clusters and superclusters of galaxies into a vast, intricate cosmic web. They're among the largest known structures in the universe and play a fundamental role in its overall architecture. The formation of galaxy filaments began soon after the Big Bang. In the early universe, slight density fluctuations in the primordial matter distribution acted under the influence of gravity, pulling matter together into increasingly complex structures. As gravity continued to pull matter into denser regions, long, thin filaments